All right, let's dive into some fascinating mechanical magic that keeps modern aircraft functioning smoothly, even when things go totally wrong. Today, in this explainer, we're looking at aircraft pneumatic power systems.
Picture this. You're cruising at 30,000 feet, and out of nowhere, the airplane's primary hydraulic system fails. Pretty high-stakes scenario, right? I mean, how does that massive, heavy landing gear actually come down safely? Well, the answer is the ultimate fail-safe, the pneumatic system. It's this invisible hero waiting in the wings, and today, we're going to see exactly how it saves the day.
So, here's our roadmap for today. 1. Powering the aircraft. 2. Air versus liquid. 3. Sourcing the compressed air. And 4. We'll look inside the air compressor. Section 1. Powering the aircraft. Okay, so before we really get into the how, we kind of need to understand the sheer variety of heavy lifting these systems do up there in the sky. While some aircraft use high-pressure pneumatics as their main power, a lot of the time, they serve as a vital emergency backup. We're talking about slamming on the brakes, opening and closing massive doors, and even driving other critical stuff like hydraulic pumps and alternators. But most importantly, it operates the emergency devices. When the primary systems go totally dark, pneumatics step right up into the spotlight to make sure the plane can land safely. Moving on to Section 2, Air versus Liquid. Now, you might be wondering, why use air? Hydraulics and pneumatics are actually super similar mechanically, They both transmit power in a confined space, but there's one massive difference. Hydraulics use fluid, which is completely incompressible. Imagine trying to squeeze a sealed full water bottle. It just doesn't give. Pneumatics, on the other hand, use gas, like air, which is highly compressible. Think about squeezing a balloon. As our source notes point out, you can compress a volume of air super tightly, and that trapped, pressurized energy is exactly what gives pneumatics its serious mechanical punch. And that compressibility, it's exactly why aircraft engineers value pneumatics so highly. These systems are inherently way lighter than hydraulic systems. Because they just rely on the surrounding air instead of heavy stored fluids, they literally don't need all the heavy fluid reservoirs, manual hand pumps, complex accumulators, or the bulky engine-driven power pumps just to build normal pressure. And in aviation, shedding weight is everything. Lighter systems mean less fuel burned, greater efficiency, and a lot more room for payload. All right, Section 3, Sourcing the compressed air. So we know air is light and powerful when it's compressed. But how does the aircraft actually get that air into the system to perform all these heavy tasks? Well, one primary way to get compressed air, or sometimes nitrogen or carbon dioxide, is just filling an emergency bottle while the plane is safely on the tarmac. The journey starts at a ground charging station, flows right through a charging valve, gets trapped in the emergency air bottles by a shutoff valve, and then it just waits. It waits until the exact moment it's needed by the actuators to, say, push down the landing gear. But there's a huge catch here. If this ground-charged emergency bottle is your only source, you can't recharge it mid-flight. Once you use it, it's gone until you land. To solve that pretty major limitation, engineers designed continuous sources. Take a look here. We can compare that limited ground-charged system with continuous in-flight solutions. During a flight, pneumatic power can actually be continuously supplied by something called bleed air. This is air drawn directly from the aircraft's engine's very own compressor stage. Or, alternatively, the aircraft might use a dedicated air compressor hooked up to the engine gearbox. This setup draws fresh air straight from the atmosphere outside, compresses it, and feeds it right into the storage bottles. The result? A steady, constantly replenishing supply of power mile after mile. And that brings us to Section 4, inside the air compressor. Let's dive into the actual mechanical how of these incredible devices that recharge the system high above the clouds. What we're looking at is a single-stage reciprocating compressor. Focus right on the center, you've got a drive shaft that's continuously turned by the aircraft's motor. As it spins, it moves the pistons back and forth inside those cylinders. It basically pulls air in through a filter, crushes it down inside the cylinder, and shoves it out through check valves into a high-pressure line, sending it straight to the air storage bottle. It is just this continuous, rhythmic pumping action, literally capturing the atmosphere itself. But what if your systems demand even higher operating pressure? Well, that's where the two-stage air compressor comes into play. Here, the air gets compressed not once, but twice, moving from stage 1 into stage 2 for maximum pressure. But take a close look at that distinctive red zigzagging line right at the top connecting the two stages. That is a highly specific and absolutely crucial component. That little zigzag line is the intercooler. This relies on a pretty basic law of physics. When you compress air, you generate a massive amount of heat. And if the air gets too hot, it expands, which makes it way harder to compress further. That puts a terrible strain on the engine driving the compressor. The intercooler brilliantly solved this. It cools the air down as it travels between the first and second stages of compression. By pulling that heat out, the intercooler dramatically reduces the power required to drive the compressor. It's just an incredibly elegant and efficient piece of engineering.
Looking through the actual handwritten notes from our source material, there's this fantastic little note in the margin that simply reads, "Usually a backup nowadays." And honestly, that perfectly sums up what we've learned in this explainer. While some aircraft do rely heavily on them, in most modern commercial aviation, high-pressure pneumatic systems are the ultimate understudy. They're incredibly lightweight, they don't need heavy fluids, and they pull their power right out of thin air. They just wait patiently in the background, fully pressurized, totally ready to deploy the landing gear or hit the brakes the exact second the primary systems fail.
So next time you're sitting on a plane, just listening to the hum of the engines, think about all that pressurized air rushing through the invisible veins of the aircraft, standing guard. Which leaves me with a question for you to ponder. Next time you fly, what other invisible backup systems do you think are standing by, hidden in the wings and the fuselage, just waiting to keep you safe? Thanks for joining me to explore this today.